placed here is, and I placed it differently from your textbook. Your textbook places it, I want to say, within the first 5 pages of that chapter, if not the first 4. And the reason it's placed there in the context of what Sorrell does in chapter 24 is that it's an example of a method of making alpha, beta, and saturated systems. Okay, so the whole chapter is focused on how you utilize alpha, beta, and saturated systems. That's what we talked about yesterday with the conjugate addition, all that. But in the beginning of Sorrell, one of the things I didn't cover is what methods do you have of making them? And I tinged on it yesterday, and I said, well, we just learned in the preceding chapter the aldo reaction. And if you do the aldo reaction and do a condensation, you make alpha, beta, saturated aldehydes or ketones. Well, there are other methodologies, but the other one that I want you to be aware of is the Mannich reaction, okay? And again, I really wanted to present this at the very end. This is kind of cool. It's kind of cool in the sense that yesterday I also talked about why we use N-amines as well as imines. What's very interesting about this reaction, it kind of looks at that, but in a different context. Chemists are really, in the past, I would say 20 years, chemists, organic chemists in particular, have been very interested in this type of reaction. This is an example of what we call a 3-component reaction. So notice that I have 3 molecules that are reacting. I have a ketone, I have an aldehyde, and I have an amine. Okay? And so years ago, chemists about 20 years ago were very interested in developing libraries of pharmaceuticals. And one way of thinking about pharmaceuticals is something called combinatorial synthesis, which basically says, could one make libraries of molecules to screen for a new drug by basically taking a ton of different ketones, throwing it with a ton of different aldehydes, a ton of different amines, and see what you get? Of course, they systematically varied one at a time, but they did this in different reaction. So if you think of a tray with a bunch of test tubes, this is how it was done, where one variant, we varied the ketone, and then in another variation, we varied the aldehyde, and then what they did is they took these samples and see if any of these compounds exhibited some type of an effect on a particular disease or ailment. Okay, so I just wanted to point that out. In this reaction, what you have is, again, you have an aldehyde and ketone, and you have a secondary amine with catalytic amounts of acid. Okay, so there are things I need you to think about here, and some of the things I need you to think about is the following. Right going into this, what I want you guys to ask the question: what is more electrophilic? If the amine here is going to be my nucleophile, because it's the only one that has a lone pair of electron that that's going to be basic enough or nucleophilic enough, which one of these would you anticipate would be the better electrophile? The ketone or the aldehyde? The aldehyde. Right? So one of the first steps you're going to see me do is react this aldehyde with this amine. Okay? So what do you know from what Dr. Schwann's taught you? How do amines react with aldehydes in the presence of HCl? What's formed?
Iminium ion.
And an iminium ion, okay? And recognize iminium ions from the context I shared with you yesterday. Are they nucleophiles or electrophiles?
Electrophiles.
Exactly. So remember I said yesterday that N-amines are always nucleophiles, but imines or iminium ions are always electrophiles. So all we're going to be doing is taking these two guys first, reacting it through the mechanism you already known from Dr. Schwann, and making an iminium ion. Okay? May I ask, was that on your exam too? Or was that exam 1?
Exam 1. Yeah, exam 1.
Okay, because you did aromatics in exam 2, correct?
Yes.
Okay, so it's a reaction that you've learned a lot, in the first couple of weeks, and again, we're seeing it again in this context. So again, I don't want you to forget about the chemistry you learned in the aldehyde and ketone chapter. Okay, so if I'm making an aminimine here, which is going to be an electrophile, I need a nucleophile, right? And so the nucleophile I'm going to be using has to come from the ketone. Now, look at the reaction conditions. What do you think the structure of that nucleophile is going to be? Am I going to form enolates?
No.
Why not?
Because it's under acidic conditions. It can only form an enol.
Right. So, thank you. So basically, what we're going to do in the mechanism, and nothing you have not seen, is first we're going to take the aldehyde and react it with the amine to make an aminimine, which you've learned. And then we're going to basically tautomerize this, because we're an acid, to the enol. And the enol is going to function as my nucleophile. So notice that what I have here is a new carbon-carbon bond being formed. This carbon here is going to be what? My nucleophile or my electrophile in that polar covalent. So, right now what we're doing is we're not doing radical chemistry. We're basically taking nucleophiles and reacting with electrophiles. So basically we have positive reacting with negatives, right? So is this blue positive or negative? It's negative. It's adjacent to a carbonyl, right? So obviously that's going to come from the enol there. So this carbon shown in magenta has to be electrophile. And of course it's coming from the enol. So all we're going to really do is make an aminimine first, tautomize this to a enol, and then we're making a carbon-carbon bond between the enol and the aminimine. Okay, so again, it's just an opportunity just to showcase some of the mechanisms you learned. So here we go. Okay, so the amine comes in, attacks the aldehyde, and forms this tetraintermediate. Again, we're leaving out steps. Obviously, this is not OH first, so I should have a proton transfer. And then we make this into a good leaving group, and then the amine comes in, kicks this off to make this aminium cation. Okay, so that's the first two that's reacting. Now the ketone in acid, again, I'm not showing the whole mechanism here. I'm not showing all the steps to make the enol. So I'm just showing this guy going to the enol. Once I have the enol will react with the aminimine. So if you permit me, I'm going to push this electron here and here, and I get what's called a manic base. Okay, so again, it is a 3-component reaction, but really what we're doing is first taking 2 of them to make an aminimine and then reacting some. Okay, so it's not that bad of a deal. I took this mechanism from your book because it's a little bit more greater detail. Okay, so here it's showing that you not all the steps of the mechanism. In fact, I skipped this in the Sorel. I think I did. I can't recall, but these, within the chapter, there was a question: propose the mechanism for this transformation. I think all you guys should do. But again, amines eventually react with aldehydes to go to this intermediate here. This is called an aminal. Okay, aminals then basically can react with acid and make the OH into a good leaving group, in which this nitrogen comes in, attacks, and makes this aminimine to lose water. Okay. Here is the mechanism for enol formation. Again, first step is we protonate this carbonyl to make this a good electrophile, and then the proton leaves to make this enol. And then finally, this guy comes in, attacks here, and gets that. Okay? And then subsequently, you can lose that proton, and you get that manic base. All right. Now, just a couple things here. You can take formaldehyde and treat it with certain types of amines. If you specifically take dimethylamine and do this, you could actually isolate this. And this salt here is a famous salt. Escher Mosher won a Nobel Prize for his work in developing a synthesis He won a Nobel Prize. There was two awards that year, and one award was to I can't think of, it was a Harvard chemist, and Escher Mosher was in Switzerland, and they both got shared a Nobel Prize for coming up with the synthesis of vitamin B12, which was basically a very difficult synthesis at the time. But you know, Escher Mosher was very well known, and he can, what's that? And he developed, you could actually buy this salt commercially. It's called the Escher Mosher salt. It's all it is an ammonium ion. Okay. So then what you could do, and the reason that really, again, the reason to teaching you the Mannich reaction is that it in principle can be used to generate alpha, beta, and saturated systems. So if you notice, this product here is an alpha, beta, and saturated ester. Okay. So up to this point, the allo reaction, we can only make alpha, beta, and saturated aldehydes and ketones. Here is an alpha, beta, a method to make an alpha, beta, and saturated ester. All right. So how does this work? Well, in this example here, I'm going to use a strong base such as aldehyde to preform the enolate, right? So one of the things we talked about is aldehyde makes 100% formation of the enolate because it's a strong base. So once I treat this with this ester here, this is the alpha proton, all of it will go to the enolate. Now that I have the enolate, that's my nucleophile, that will react with this electrophile. So electron here comes here, attacks that, and I get this guy. Okay? So not a very difficult thing. So where's the new methodology? The new methodology is the following. In the second step, in order to basically eliminate this species to make this double bond here, what you first have to do is methylate it using methyl iodide to make the nitrogen as a quaternary salt. Okay, so recognize this nitrogen has basically 4 alkyl groups around it, in which 3 of them are methyls. Okay, and this is very important for one of the, and I'll showcase this in a moment. Now, let me go back here just to mention a point here. Why did we protonate this OH here?
Yeah, so that it turns into an H2O, which is a better leaving group than OH.
So basically, what I want you to start to rationalize and conceptualize is what you learned in the first semester is how one makes good leaving groups. So leaving groups are always conjugate bases of very strong acids, right? And so that was the whole premise around it. And so one of the first things you learned in the first semester course is that alkyl halides are great leaving groups because if I have an alkyl iodide or an alkyl bromide, the leaving group is bromide and iodide, and those are conjugate bases of HBr and HI, which are very strong acids. Okay. Now, what you also learned is another effective way to make a good leaving group is if you protonate it first. And notice that if I protonate this OH here, now I have OH2+. This is a good leaving group, and the other way I want you to think about this is a good leaving group, of course, because it's now a conjugate. The leaving group's a conjugate base of hydronium ion, right? But what I want you guys to start to see, another process that you guys did was anytime you protonate a species here, you made a system that has a positive. And once you have a positive, that becomes a good leaving group because it leaves as a neutral species. Right? So another way to look at this, yes, we're protonate this, yes, it's a good leaving group. But why is it a good leaving group? Well, it's protonated here. If it was to leave, it leaves as water, which is very stable. There's no charge on it. Well, the same thing applies here. The reason we're methylating this is that now I have a nitrogen with a positive charge. It should be a good leaving group because if it leaves as a pretty stable base in trimethylamine. Okay, this is an example of another elimination. In general, we can eliminate species that have a leaving group that's positive. Okay, you've been doing this with OHs to convert it in acid to water. Another way is to convert this nitrogen to a good leaving group by making the quaternary salt. Okay, so basically I'm doing this to make this guy into a good leaving group. All right, now notice that I take a mild base. It's such a good leaving group, and this proton is relatively acidic because of, this is a good leaving group, and I have the fact that this proton is adjacent to a carbonyl here. All I need is to use bicarbonate. Bicarbonate will come in, abstract this proton. Once this proton is abstracted, that electron pair comes here and basically eliminates this guy. Okay? Now, one other thing. Recognize that in this step here, this is an E2 mechanism. I'm abstracting this proton. This is the alpha carbon. The leaving group is on this beta carbon here. Okay? So my question here is, why can't I abstract protons on this methyl group? Why is the leaving group only here? And why can't it go in the opposite direction?
What was the question?
So if I'm deprotonating this guy, making this into a leaving group, okay, why do I have methyls here? Well, let me just give you the answer. The reason for the methyls here is that, remember, in any good leaving group, right, in order to have a E2 elimination, you have to have 2 carbons. So I have, since I'm only, the nitrogen is attached to methyl, if this was ethyl, then I would have to consider it as a secondary elimination. Obviously, this is the most acidic proton, but this is designed so specifically, the only way this could eliminate is in this direction, because I have a potential of making a double bond here. With methyl groups here, I can't make an alkene because there's only 1 carbon on each on each nitrogen of the methyl groups. Okay, so I'll try to show that. Let me see. What I'm saying here is that now that you understand this is as a leaving group because it's nitrogen, in principle, let me do it this way. Base can come in and abstract this proton here in an E2 elimination. Okay? What I'm getting at is if I now replace this with the methyl group, notice that a base can't come in because I have no 2 carbons here. I only have 1 carbon. So my point here is the reason that Eskimo should develop this salt is that there's methyl groups. So I am forcing it to eliminate always by abstracting this proton here. So let me go back to the PowerPoint. Let me toggle this back.
So it's not able to form an enolate-like structure.
No. What I'm saying is there's no way that these methyls can eliminate because there's no beta carbon. There's only 1 carbon here.
Oh, okay.
If these were ethyl groups, then I would have to consider what I just wrote on the document camera. But because he's using methyl groups here, right? The direction has to be, the only beta proton I have is to the leaving group here, is this alpha proton to the carbonyl. So the direction of this is always going to be where I'm abstracting this proton and undergoing the elimination to make that. Okay, so again, if you recognize this, here is the Mannich reaction. Okay, so I'm going to make an amine salt, and then I'm going to rely on either an enolate or an enol. In the classical case for an enol, you use in the classical case for a manic, you use an enol. In this case, we're using a preformed enolate. Now that I have an enolate, if I introduce the salt, I make this manic base. So the first step is the manic reaction. Okay? So the new part here is, now that we know how to make the manic reaction, how can I use it to basically convert it into an alpha beta unsaturated system? Well, what I'm sharing now is that there's two steps to it. The first step is to methylate that nitrogen to make it into a good leaving group as a quaternary salt. The second step is to add base to perform an E2 elimination. In this case, I'm abstracting the proton at the alpha position. That proton is going to take this and this. So anytime that I have a base, so what I want you guys to recognize is, if I do this type of methodology, or if I have this, if you see a methyl group here, please recognize that's to make this into a good leaving group. And then if you see in the second step that I have some type of base, it may not be bicarbonate, it could be any other base, that is to undergo E2 elimination. So it's a two-step process to go from the manic product into the alpha beta unsaturated product. Yes, thank you, Marco Woodward. So the other person that won the Nobel Prize is Robert Woodward, who was a very famous chemist. Thank you, Marco.
Would you mind flipping back to the piece of paper one more time?
Absolutely.
Thank you.
Absolutely. Okay. So if I go to that example, did you have a question here?
No, I just wanted to see what you're talking about. Now I get it. Thank you.
So that's what I mean here. Again, let me draw the structure. I think it looks something like this. Okay.
Could you put the picture up a little bit?
So in this methodology, notice that in the first step, we're using the Escher-Mosher salt, which is giving me a nitrogen with two methyl groups. Okay? And the next step is to basically treat this with methyl iodide followed by base. Okay? Now, in step one, so if I ask you any questions, you're going to see something like this. Okay? But I want you guys to think about this process and see it as step one. All that does is makes this into a good leaving group. Okay? Step two basically takes a base. I'll push the arrows because the arrows were not on that slide. And I'm making a double bond there and a leaving group. Okay? So this is my E2 elimination step. Questions?
Would you mind moving the paper up just a little, please? Thank you.
Any other questions? Good. All right. So that's really the context of why the manic reaction is taught in this section, in that again, it's methodology that permits one to make an alpha beta unsaturated system. So now that you have this double bond, you could do micro reactions with it. Okay? All right. So let me go ahead and open up the next PowerPoint.